In this video, you will learn how to control a motor with your Arduino. The code to get started doing this is very simple. I'm actually running the exact same code here that I would use to blink an LED. As you can see, that makes the motor spin for 1 second and then stop for 1 second. However, the circuit to control the motor is much more complicated, so we'll take our time to explain what this circuit is for and how to build it. In addition to your Arduino and breadboard, you will need the L293D H-bridge, 4 AA batteries and the 4xAA battery holder, a DC motor, and assorted jumper wires. Remember that short jumper wires are better for making connections on the breadboard, and longer jumper wires are better for making connections from the breadboard to the Arduino. Now, you might wonder why all these extra circuit parts aren't necessary at all, and why you can't just plug the motor directly into the Arduino pins like you could with an LED. To understand that, we need to talk a little bit about electrical current, or the amount of electricity that is flowing through a circuit. We measure electrical current in a unit called amps. 1 amp is equal to 1,000 milliamps. An Arduino digital pin can provide up to 20 milliamps, which is enough to power a tiny LED. However, it's not enough current to directly power a motor. Even small motors can use hundreds of milliamps to operate. Therefore, to power the motor with an Arduino, you need an external battery pack that can provide more current to drive the motor. We'll use an additional circuit part called a motor driver, also called an H-bridge, to interface between the Arduino and the motor. The H-bridge allows you to use low-power control signals from the Arduino to turn the motor on and off, but it draws the power for the motor from the external battery pack. I am going to demonstrate how to build the circuit using a computer program called Tinkercad Circuits, because it makes it a little easier to see exactly where everything goes in the breadboard. You can follow along with your physical Arduino, or create an account at tinkercad.com and follow along in a web browser. Let's start with the Arduino and the breadboard. We're going to need to make good use of the breadboard's power buses in this project. Your entire circuit will need what's called a common ground, meaning they should all be connected to the ground buses and ultimately to the Arduino ground. So I'm going to use a jumper wire to connect one of the ground buses to the Arduino ground pin, and then use another jumper wire to connect to the ground bus on the other side of the breadboard, because remember, the opposite side ground buses are not connected internally on the breadboard, as you can see from the highlighting here in Tinkercad. We are also going to need the 5-volt supply from the Arduino, so I'm going to connect that from the 5-volt pin over to the power bus on the right-hand side of the breadboard. However, I am not going to connect the power buses on opposite sides of the breadboard because I am ultimately going to have 2 different voltages in this circuit. I'm going to have 5 volts from the Arduino and 6 volts from my external 4xAA battery pack. So while you will want a common ground for those 2 different voltages, you do not want to short circuit the positive voltages together. So again, do not add a jumper wire connecting the opposite power buses. We will have 2 different voltages connected to those. Next, let's add the H-bridge. We are using a specific H-bridge in this project called the L293D. So if I say H-bridge, motor driver, or L293D, those terms are all pretty much interchangeable. The H-bridge is a type of integrated circuit, meaning it has multiple circuit parts inside a single plastic package. This type of package is called a dual inline package because of the 2 rows of pins. As you can see here, if I switch back to footage of the physical breadboard, the package is sized such that it fits straddling the gap in the middle of the breadboard. If I switch back here to Tinkercad, you can see how it will snap into place straddling the gap in the middle. So it's important to put it across that middle gap and not entirely on one side of the breadboard, because again, remember how breadboard holes are connected, you would then be short-circuiting pins on opposite sides of the chip. So make sure you put it in the middle of the breadboard with the notch at the top of the chip facing up. It's important not to get it inverted because then you will get all of the pins backwards. So make sure the notch or dot at the top of the chip are facing up towards the top of the breadboard. Now, by convention, the pins on a dual inline or dip package are numbered counterclockwise starting from the top left. So for example, the top left is pin 1, we go down to pin 8 on this side, then circle over to the other side to pin 9, all the way up to pin 16. You have to be careful because depending on where you put the chip in the breadboard, the pin numbers are not going to match up with the row numbers in the breadboard. You can look up information about the pins in a document called the datasheet, which contains a lot of information about the part, how to use it, and what the pins do. So here I have a diagram that labels the numbers for those 16 pins, and a table that explains what they are each for. However, you don't need to worry about looking at the datasheet for this video. I will walk you through the pins that we are going to use, what they're for, and how to connect them. The first things we will connect are the 4 ground pins, which we can see labeled if we hover over the pins here in Tinkercad. The H-bridge has 4 ground pins instead of just 1 because this helps it dissipate more heat. Things with a lot of current flowing through them tend to get hot. So I'm going to add a jumper wire from each row that has a ground pin over to one of the ground buses. This completes all of my ground connections. Next, I'm going to connect what's called the logic voltage. This is what enables some of the internal operation of the chip, but it's not the voltage that will ultimately power the motors. So I'm going to add a jumper wire from pin 16, the top right pin here, which is labeled power 1 in Tinkercad, over to the power bus that I had previously connected to 5 volts on the Arduino. Next, I'm going to connect the enable pin. This is a pin that we can use to control the speed of the motor if we don't want to run at full speed by connecting it to one of the Arduino's outputs. However, for now, we're not going to worry about that. We're just always going to run the motor at full speed, so I'm going to use a jumper wire to connect that directly to 5 volts. We now have 4 pins left on this side of the chip. 2 output pins, which we will connect to the 2 motor wires, and 2 input pins, which we can connect to the Arduino to control the direction of the motor. However, for now, we're only going to worry about spinning the motor in one direction, so we're going to connect one of those input pins directly to ground, so it's always at 0 volts. I'm going to use a jumper wire to connect the other input pin over to Arduino pin 12, which we will use to turn the motor on and off. There isn't a specific convention for what color you need to use for input and output wires, so I'm just going to choose blue for my output. Now I'm ready to connect the motor. Don't worry if the motor in Tinkercad doesn't look exactly like your physical motor, the basic idea is the same. The motor has 2 wires, and when electrical current flows through them, the motor will spin. I'm going to connect these 2 wires to the 2 output pins on my H-bridge. It doesn't really matter which wire you connect to which pin, because this is just going to change the direction that the motor spins. So if you want the motor to spin the other way, you can always reverse the wires later, and once we connect the second input to the Arduino, you can also change the direction the motor spins using code. We are missing one more connection here. Remember that the motor is not going to be powered by the 5 volts from the Arduino, it will be powered by an external battery pack. We need to connect that battery pack to pin 8, labeled power 2 in Tinkercad, on the H-bridge. So I'm going to add a 4xAA battery pack to my circuit, move that over to the side, and connect it to my breadboard. Remember that the entire circuit needs a common ground, so I am going to connect the black or negative wire from my battery pack to the ground bus on the breadboard. However, I do not want to short circuit the positive voltage from the battery to the positive 5 volts on the Arduino. So I am going to connect that over here to the power bus on the left side of the breadboard, but I am not adding a jumper wire connecting the 2 different power or positive voltage buses, because that would create a short circuit between them. So again, remember, this is a very important point. Your entire circuit needs a common ground, so everything is connected to the ground buses, to the Arduino's ground pin, and to the negative terminal on the battery pack, but you do not want to short circuit the positive voltage from the battery to the positive 5 volts from the Arduino. Once you've done that, you can add the final jumper wire connecting pin 8, labeled power 2 in Tinkercad, to the power bus that has the positive voltage from your battery pack. We are going to leave the other pins on the H-bridge disconnected for now. We don't need them until we add a second motor. Now, that was a lot of wiring. This is a good point to pause the video and carefully double check your circuit and make sure you have each pin on the H-bridge wired correctly. I am also going to walk you through all of them pin by pin, again going by the pin numbers, starting counterclockwise in the top left. Pin 1 is not connected. Pin 2 is not connected. Pin 3 is not connected. Pin 4 is connected to the ground bus. Pin 5 is connected to the ground bus. Pin 6 is not connected. Pin 7 is not connected. Pin 8 is connected to the power bus that is connected to the positive voltage from the battery pack. Pin 9 is connected to the 5-volt power bus. Pin 10 is connected to the ground bus. Pin 11 is connected to one wire from the motor. Pin 12 is connected to the ground bus. Pin 13 is connected to the ground bus. Pin 14 is connected to the other wire from the motor. Pin 15 is connected to pin 12 on the Arduino. And pin 16 is connected to the 5-volt power bus. Once you have double-checked your wiring, you are ready to write code to turn the motor on and off. In Tinkercad, you can open the code window. If you're using a physical Arduino, you can open the Arduino IDE. As I mentioned earlier, this is exactly the same code that you would use to blink an LED. First, we declare a variable saying which pin we're going to use to control the motor. In our setup function, we use the pin mode command to set that pin as an output. Then, in our loop function, we use the digital write command to set that pin high, wait for a second, use the digital write command to set that pin low, wait for another second, and repeat. That is going to repeatedly turn the motor on for a second, then off for 1 second. In Tinkercad, I can hit Start Simulation, or with a physical Arduino, you can upload your code, and you should see the motor spin for 1 second, then turn off for 1 second, repeatedly. Again, if I reverse the motor's wires, that is simply going to reverse the direction that the motor spins. So if I switch the red and black wires here in Tinkercad, and then start the simulation again, we will see that the motor is now spinning the other way. If you haven't already, pause the video here, take the time to type in this code, upload it, and make sure your motor works. If your motor does not spin, you can confirm that your motor is not broken by connecting it directly to power from the battery pack. I can do that here by moving the motor's jumper wires directly over to the power and ground buses. If you do this with a physical circuit, the motor should power up immediately. If I hit Start Simulation in Tinkercad, we should see that the motor just spins continuously. It does not turn on and off because it is not being controlled by the H-bridge and the Arduino right now. Again, it is just connected directly to power from the battery pack. So that is a good way to confirm that your battery pack and your motor are both working. If your motor does not spin when you do this, double check to make sure you have all of your batteries inserted into the battery pack correctly, make sure you're using fresh batteries, and make sure all of your wires are firmly pressed into the breadboard. Now, ideally, we would like to be able to reverse the motor's direction using code. For example, if you are building an Arduino car and you want it to drive in reverse, you can't really grab it and rearrange the wires every time you want it to change direction. So we're going to do that by making use of the second input on the H-bridge. Previously, we had used a jumper wire to connect that input directly to ground, so it's always at 0 volts. We are going to delete that wire and connect the pin to one of the Arduino pins instead. So I'm going to use a jumper wire to connect Arduino pin 11 over to my input on the H-bridge. Now we're going to modify the code to use 2 different pins to control the motor's direction. I'm going to change my code a bit and call this backward pin. That's the pin that we'll use to make the motor spin backward. I'm also going to edit my comment so it matches what I'm calling that variable. I'm going to create a new variable for what I'll call forward pin. That's going to be pin 11. That's the pin that we'll use to make the motor spin forward. Now, to understand how to use these variables, we need to talk about what happens when we set them high or low. That's easier to explain using a table. If the forward pin is set high, while the backward pin is set low, the motor will spin forward. If the forward pin is set low, while the backward pin is set high, the motor will spin backward. However, if both pins are set high at the same time, or both pins are set low at the same time, the motor will stop. Here is modified code that makes the motor spin forward and stop using both control pins. First, I declare both pins as variables. Then, I use the pin mode command to set them both as outputs. Then, I use two digital write commands to set the forward pin high and the backward pin low to make the motor spin forward. Then, I use two more digital write commands to set both pins low to make the motor stop. Here is a programming challenge for you. Add code to the program so the motor spins forward for 1 second, stops for 1 second, and then spins backward for 1 second before repeating the loop. Pause the video here and try it out. Here is an example solution. I'm going to copy and paste the code I wrote to make the motor spin forward to the end of my loop. Then, I'm going to modify my digital write commands to make the motor spin backward. I'm also going to change my comments to be consistent with what my code's doing. To make the motor spin backward, I'm going to set the forward pin low and the backward pin high. Again, I'm going to change my comments to match the code. Now, when I upload the code, I should see the motor spin forward for 1 second, stop for 1 second, spin backward for 1 second, and then repeat. So here we go. Spinning forward, stopping, spinning backward, and then immediately spinning forward again, repeating that in a 3-second cycle. This is a good time to introduce a new programming concept, writing your own functions. Copying and pasting lots of lines of code inside your loop can get messy, especially if you're going to use them repeatedly. For example, what if I wanted to have my motor stop again after I have it spin backwards here? I would have to copy and paste these digital write commands. Instead, I can move these commands into a separate function that I can call from within inside my loop. The code will then jump down, do what I tell it to do in the function, and jump back to the loop. If that doesn't make sense, don't worry, we'll demonstrate it with an example. Let's say that I want to write a function to stop my motor. I'm going to type void, then give my function a name. I'm going to call it stop motor. Open close parentheses, open, and then close curly brackets. This tells the Arduino that I have a function called stop motor that does not return anything, meaning this function isn't doing any calculations and giving a number back to the loop. That's what the void means. And it also doesn't take any arguments or numbers that are inputs to the function, so we leave the part in the parentheses here blank. We can write more advanced functions that do calculations using inputs and then give an output back to the program, but we're not going to worry about that yet. The code that executes in the function is going to go inside these curly brackets. The code that I want to happen there is these two digital write commands, so I'm going to cut them out of my loop and paste them inside my stop motor function. Now, if I want to call this function from inside my loop, I simply type stop motor, open close parentheses, and then end that line with a semicolon. So the flow of my program is now going to be that I will enter the loop, it will do these digital write commands to set the motor spinning forward. It will then call the stop motor function, so it will jump down here, do these two digital write commands, and then once this function is done, it will jump back up to where it left the loop. Next, it will do the delay command, and then it will continue on and spin backwards. So we can see that if I run this program, it will behave exactly the same as it did before. The motor spins forward, then stops for a second, spins backward, and immediately switches to spinning forward again. Now, if I want my motor to stop somewhere else, again, for example, if I want it to stop after it spins backwards before it starts spinning forward again, I just need to call my stop motor function again. I don't need to copy and paste two different digital write commands. So moving that code down here into a function helps keep my loop neater and more organized when I'm reading the code. So now I can run this program and we will see the motor spin forward, stop for a second, spin backward, then stop for a second, then repeat. So again, I am cleaning up my loop and making it neater by using functions that have a purpose that I'm going to need to use repeatedly, which saves me from copying and pasting this code multiple times inside my loop. So here is your next programming challenge. Write your own functions to make the motor spin forward and spin backward. Then replace the digital write commands inside your loop with calls to those functions. You should be able to do this following the same procedure that I used to write the stop motor function. Pause the video here and try it out. Here is an example solution where I have written two additional functions called spin forward and spin backward. Each function contains the digital write commands to make the motor spin forward or backward. Then, inside my loop, to make the motor spin, all I need to do is call those functions. Again, this keeps the code inside my loop much neater if I want to use these functions repeatedly, because I don't have to copy and paste all of these digital write commands. Remember that you can make up your own names for the functions. You don't have to use the names that I used here if other names make more sense to you. Finally, you might wonder, what about all those delay commands? We have 4 of them inside the loop. Don't we want to avoid copy and pasting those as well? And while you don't have to, you could also include the delay commands inside the functions. To do that, you need to pass an argument or input to the function, like this. Say we want the stop motor command to stop the motor for a certain amount of time. I'm going to give the stop motor function an input that I'm going to declare as an integer, just like I would with a variable, and I'm going to call that variable delay time. Then I'm going to include a delay command inside the function that delays for the variable delay time. Now, when I call the stop motor function, I need to pass the argument or send it that input. So for example, if I want it to delay for 1000 milliseconds, I would type 1000 here. Now I can delete this delay command because that delay command is now included in the function. I'm going to do the same thing down here when I call stop motor a second time, but let's say that I want to use a different time. This time I'm going to make the motor stop for 2 seconds. So I'm going to type 2000 here, and again, delete this extra delay command. Now, each time the stop motor function is called, it will pass this number to the function, the delay time variable will take that value, and then it will delay for that amount of time. This makes it easy to use a single line of code to make the motor stop for a certain amount of time, because it calls this function, which contains the multiple lines of code that are needed to make that happen. So here's your final programming challenge. Move the delay commands inside the spin forward and spin backward functions as well. Pause the video here and try it out. Here is an example solution. I have modified both my spin forward and spin backward functions to also accept an input called delay time, and I've added the delay command for delay time milliseconds to both functions. This lets me get my loop down to just 4 lines of code, where I can call each of my 3 functions, spin forward, stop motor, and spin backward, for a certain amount of time. So, if I want to program different behavior for my motor, like alternating spinning and stopping for different amounts of time, that makes it much easier and neater in my loop, because I only need to use this single line of code for each function. All of the messy code is down here inside the functions, but once I have established these and gotten them working, I don't really need to worry about them anymore. I can just call them from my loop. These functions become increasingly useful as you write more complex code. For example, if you are building an autonomous Arduino car and want to have functions to make it drive forward, drive backward, turn left, turn right, and stop.